Max Planck's discovery of quantum theory, which would later revolutionize the entire field of physics, began with a fundamental problem that had plagued scientists for decades: the issue of blackbody radiation. To understand the magnitude of Planck's breakthrough, we must first delve into the state of physics before his discovery. At the close of the 19th century, classical physics had explained many phenomena with impressive success. From Newton's laws of motion to Maxwell's equations describing electromagnetism, scientists believed that the universe operated under a set of continuous and deterministic laws. Yet, despite the successes of classical physics, there was a fundamental issue that could not be solved by the existing theories. This issue was related to the radiation emitted by hot objects, a phenomenon known as blackbody radiation. A blackbody, in scientific terms, refers to an idealized object that absorbs all electromagnetic radiation that falls on it and radiates energy at a characteristic spectrum depending on its temperature. The problem, known as the ultraviolet catastrophe, arose when scientists attempted to calculate the spectrum of radiation emitted by a black body at high temperatures using classical physics. According to classical theory, as the temperature of a black body increased, it should emit more radiation at shorter wavelengths, including ultraviolet light. However, experimental data showed something entirely different. At high temperatures, the intensity of radiation did not increase indefinitely as predicted, but instead reached a peak and then decreased at even shorter wavelengths. This discrepancy between theory and observation was a glaring issue that seemed to defy the well-established laws of classical physics. It was against this backdrop of confusion and uncertainty that Max Planck stepped forward. At the time, Planck was a relatively unknown physicist who had spent years studying thermodynamics and radiation. He was keenly aware of the problem of blackbody radiation and the growing frustration among scientists as they tried and failed to explain it using the classical understanding of energy. Planck, however, approached the problem differently. Rather than attempting to apply classical theories to the radiation problem, he considered the possibility that energy itself might not behave in the continuous manner that classical physics assumed. In 1900, Planck proposed an entirely new approach, one that would become one of the most important and controversial ideas in the history of science. His hypothesis was simple yet profound. He suggested that energy is not emitted or absorbed continuously, but in small discrete packets, which he called quanta. Planck's idea was radical because at the time, scientists assumed that energy flowed smoothly and continuously. The notion that energy could be divided into tiny, indivisible units was completely foreign to the scientific community, and it defied the established understanding of how the world worked. To make his theory mathematically rigorous, Planck introduced a formula to describe the distribution of energy emitted by a black body. His formula matched the experimental data perfectly, solving the problem of black body radiation. Planck's equation, known as Planck's law, showed that the energy emitted by a black body at a given temperature was directly related to the frequency of the radiation, and that it followed a specific curve. This was a groundbreaking achievement, as it explained the observed radiation spectrum and resolved the ultraviolet catastrophe. However, while Planck's formula was a perfect fit for the data, his explanation for why energy was quantized was less clear. Planck himself was hesitant to fully accept the idea of quantized energy. He initially introduced the concept of quanta as a mathematical device, not as a physical reality. He was so entrenched in the classical understanding of physics that he viewed the idea of quantized energy as a temporary solution, something that worked mathematically, but didn't necessarily reflect the true nature of energy. Despite his reservations, Planck's discovery had profound implications. By introducing the idea of quantization, he paved the way for the development of quantum mechanics, a theory that would ultimately revolutionize physics. But at the time, the scientific community was far from ready to accept this radical idea. The concept of energy quantization went against everything that classical physics stood for, and many scientists were initially resistant to the idea. One of the major reasons for the skepticism was the strong adherence to classic physics, which had been so successful in explaining a wide range of phenomena. The laws of classical mechanics and electromagnetism as formulated by Isaac Newton and James Clerk Maxwell, were viewed as universal truths. The idea that energy could be quantized seemed to threaten this well-established framework. Planck's discovery, however, did not go entirely unnoticed. A few years after Planck's work, Albert Einstein applied the idea of energy quantization to explain the photoelectric effect, in which light shining on a metal surface causes the emission of electrons. Einstein showed that light, like other forms of radiation, was also quantized and could be thought of as consisting of particles, later called photons. This was a crucial step in the development of quantum theory, and it helped to establish Planck's hypothesis as more than just a mathematical convenience. Einstein's work, combined with Planck's original idea, laid the foundation for the birth of quantum mechanics. Despite the growing evidence for the validity of quantum theory, many scientists remained unconvinced. The implications of quantization were so strange and counterintuitive that the scientific community was slow to embrace them. It wasn't until the 1920s, when other physicists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger developed the full framework of quantum mechanics, that the concept of quantized energy became widely accepted. But for all the skepticism and resistance, Max Planck's discovery was undeniably one of the most important in the history of science. Planck's work opened the door to a new way of thinking about the universe, one in which energy was not a continuous flow, but rather a series of discrete packets. This idea, though difficult to grasp at first, would eventually lead to the development of quantum mechanics, which describes the behavior of particles on the smallest scales and has had a profound impact on fields ranging from atomic physics to computer science. In retrospect, it is clear that Planck's work was not just a mathematical curiosity or a temporary fix to a theoretical problem. It was the beginning of a scientific revolution that changed our understanding of reality itself. Planck's work had the power to shatter old paradigms and make way for an entirely new field of physics. Today, we look back on Planck's discovery as the starting point of the quantum revolution, a revolution that has shaped the modern world in ways that Planck himself could never have imagined. While it's true that no one believed Planck's ideas at the time, history has proven him right. The quantization of energy, once dismissed as an absurdity, is now a cornerstone of modern physics. Planck's discovery was not just a small step forward in our understanding of the natural world, it was a leap into a new era of scientific thought. The idea that energy is quantized, that the universe operates in discrete steps rather than continuous flows, has changed everything from the way we understand light to the way we build the technology that powers our daily lives. Planck's legacy is not just one of scientific achievement, but of intellectual courage, as he dared to question the established truths and propose a new vision of the world. In conclusion, Max Planck's discovery of quantized energy was a pivotal moment in the history of science. His work solved a major problem in physics, but more importantly, it opened the door to an entirely new way of thinking about the universe. Though his ideas were initially met with skepticism and disbelief, they laid the foundation for the development of quantum mechanics and reshaped our understanding of the very fabric of reality. Today, we recognize Planck as one of the founders of modern physics, and his contribution continue to influence scientific thought and technological progress in profound ways. Max Planck's discovery of the quantization of energy, which would later form the basis for the field of quantum mechanics, revolutionized our understanding of the physical world. It was a discovery that defied the established notions of classical physics, and yet, despite the initial skepticism, it laid the groundwork for the most successful and profound theories of modern physics. The story of Planck's discovery is one of both mathematical brilliance and scientific courage. It highlights the often persistent resistance of the scientific community to revolutionary ideas. To fully grasp the magnitude of Planck's work, it's important to first understand the state of physics before his discovery. By the end of the 19th century, classical physics had achieved great success. The laws of motion established by Isaac Newton had served as the foundation for mechanics, while James Clerk Maxwell's theory of electromagnetism had unified the understanding of electricity and magnetism. The theoretical framework of classical physics was powerful and universally accepted. Yet, despite these successes, certain problems remained unresolved. One of the most pressing problems facing physicists at the time was the issue of blackbody radiation. A blackbody, in the simplest terms, is an object that absorbs all the electromagnetic radiation that falls upon it and emits radiation of its own. The problem with understanding blackbody radiation lay in the fact that as temperature increased, the radiation emitted by the blackbody became more intense, but the spectrum of radiation didn't match what classical theory predicted. Classical physics, when applied to blackbody radiation, suggested that as the temperature of a blackbody increased, the emitted radiation would increase without bound at shorter wavelengths. This was known as the ultraviolet catastrophe. This predicted result did not match experimental observations, which showed that radiation intensity at shorter wavelengths leveled off at higher temperatures, and in fact, the intensity decreased beyond a certain point. It was within this context that Max Planck, a relatively unknown physicist at the time, made his groundbreaking contribution. At first, Planck approached the problem as a challenge within the framework of classical physics. He aimed to derive a solution to blackbody radiation using existing theories, but in the process he stumbled upon a radical idea. In his efforts to make the math work, Planck introduced the concept of energy quantization. Instead of treating energy as a continuous quantity, he proposed that energy could only be emitted or absorbed in discrete packets, or quanta. This idea, though initially just a mathematical tool to solve the problem at hand, would eventually become the cornerstone of quantum theory. At the time, Planck did not fully embrace the implications of his discovery. He was still deeply entrenched in classical physics and saw the quantization of energy as a mere mathematical convenience, a necessary assumption to make the equations fit with experimental data. For Planck, the idea of energy quanta was not a new physical reality, but rather a temporary solution to an unresolved problem. Despite this, his equation, known as Planck's law, perfectly described the distribution of radiation from a blackbody, resolving the ultraviolet catastrophe once and for all. The formula matched experimental data, and it immediately became a key piece of the puzzle in the study of radiation. However, the idea of quantized energy was a major departure from classical physics, which treated energy as a continuous flow. The very notion that energy was not continuous, but rather made up of discrete units, was so radical that it was met with great skepticism by the scientific community. Planck's own views on the matter were not clear-cut. He initially introduced the idea of quanta as a mere mathematical device, but over time, as more experimental evidence began to accumulate, he started to accept the physical reality of quantization. Even so, the wider scientific community remained largely skeptical, with most physicists unwilling to accept the quantization of energy. It wasn't until Albert Einstein applied Planck's theory to the photoelectric effect in 1905 that the concept of quantized energy began to gain more traction. Einstein showed that light, which was traditionally thought of as a continuous wave, could also be described as being made up of discrete packets of energy, what would later be called photons. This was another critical step toward establishing the validity of Planck's hypothesis, as it demonstrated that not only thermal radiation, but light itself, behaved in a quantized manner. Einstein's work confirmed the validity of Planck's quantum hypothesis and helped to solidify the foundations of quantum mechanics. Despite Einstein's success, many scientists still resisted the implications of quantum theory. The concept of quantized energy was so foreign and strange that it took years for the full scope of its consequences to be realized. In the years that followed, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger would build on Planck's work and develop the framework of quantum mechanics, a theory that would eventually explain not only the behavior of light and radiation but also the interactions of particles on the atomic and subatomic scales. The introduction of quantum theory represented a profound shift in our understanding of the physical world. Classical physics had been based on the idea that objects and energies could be described in terms of continuous variables, with motion and energy flowing smoothly. Quantum mechanics, on the other hand, showed that at microscopic scales, the behavior of matter and energy was fundamentally discrete, governed by probabilities and uncertainty rather than deterministic laws. Quantum mechanics revolutionized not only physics, but also technology. The principles of quantum theory have been applied in a wide range of fields, from semiconductors and lasers to quantum computers. The world of technology that we live in today, smartphones, computers, and the internet, would not be possible without the contributions of Planck and the pioneers of quantum mechanics. Yet, at the time of Planck's discovery, the full implications of his work were not understood, and the path to the acceptance of quantum theory was long and difficult. Max Planck's discovery of energy quantization was, in many ways, a breakthrough that defied the very foundations of classical physics. It was a revolutionary idea that no one believed, yet it changed the course of science and led to the creation of quantum mechanics. Despite the initial resistance and skepticism, Planck's work paved the way for a new understanding of the universe, one that would eventually reshape our view of the natural world. The legacy of his discovery lives on in the technologies we use every day and the scientific theories that continue to guide our exploration of the cosmos. The acceptance of Planck's idea was not immediate, but today it stands as one of the most important and transformative discoveries in the history of science. As we look back on Planck's contribution, it becomes clear that science is often not just about finding answers, but about challenging established beliefs and pushing the boundaries of knowledge. Planck's ability to propose a new way of thinking about energy, despite the overwhelming resistance from the scientific community, exemplifies the essence of scientific progress. In the years that followed, quantum mechanics would continue to evolve, and the world of physics would never be the same again. Today, we honor Max Planck as the father of quantum theory, whose discovery, though initially rejected, transformed our understanding of the universe in ways that no one at the time could have fully predicted. Max Planck's theory of energy quantization, though a groundbreaking discovery in the field of physics, was not immediately understood, and it wasn't until later that its true implications would be fully realized. However, the idea that energy exists in discrete quantities rather than continuously, contrary to the accepted laws of classical physics, opened the door to an entirely new way of thinking about the universe. To truly appreciate the depth of Planck's work, we need to dive into how his hypothesis fundamentally challenged the existing framework of classical physics and how it led to the birth of quantum mechanics, a theory that would revolutionize the way we understand the physical world. The first key element to understand is the challenge to classical physics that Planck's discovery represented. Before Planck's groundbreaking work, classical physics was the dominant framework for explaining natural phenomena. Classical mechanics, formulated by Isaac Newton, governed the motion of objects and the forces acting upon them. Meanwhile, James Clerk Maxwell's equations of electromagnetism described the relationship between electricity and magnetism and were successful in explaining the behavior of light as electromagnetic waves. Classical physics seemed to offer a complete and unified picture of the natural world. However, by the end of the 19th century, certain phenomena could not be explained using classical physics, and the study of radiation was one of the most glaring examples. Blackbody radiation, a phenomenon where an idealized object, known as a black body, absorbs all incident radiation and then emits radiation of its own based on its temperature, was a significant puzzle. In 1900, the problem of blackbody radiation became central to the debate about the validity of classical physics. Classical physics, particularly the laws of thermodynamics and the theory of radiation, predicted that as the temperature of a blackbody increased, the emitted radiation would increase in intensity without bound, and the wavelength shortened. This led to the ultraviolet catastrophe. Classical theories suggested that at very short wavelengths, radiation intensity would go to infinity, which obviously did not match experimental observation. In reality, the intensity of radiation reached a peak at a certain wavelength and then dropped off at shorter wavelengths, as observed in experimental data. This disparity between theory and experiment posed a significant problem and pointed to the limitations of classical physics. At the time, scientists had no way of reconciling this discrepancy, and classical theories were unable to explain the behavior of radiation at high frequencies. Planck's challenge was to find a way to explain the data that was not fitting within the classical framework. His solution was not to dismiss classical theory but to introduce a new concept, energy quantization, that would explain the observations while still being consistent with the existing laws of thermodynamics. Max Planck proposed that energy could not be emitted or absorbed continuously as classical physics suggested, but instead, Energy was emitted in discrete packets, or quanta. Planck's hypothesis was revolutionary because it directly contradicted the established belief that energy flowed continuously. He introduced the idea that energy existed in fixed quantities, or discrete units, and this concept would later become the foundation for the theory of quantum mechanics. Planck himself, however, did not initially embrace this idea fully. He saw the quantization of energy as a mathematical device, a way to make his equations work with experimental data. At that point, Planck was not yet willing to acknowledge that energy quantization was a fundamental property of nature. Despite his own reservations, Planck's mathematical formula, now known as Planck's law, perfectly matched experimental observations of blackbody radiation. The law demonstrated that the radiation emitted by a blackbody could be described by a distribution curve that depended on temperature and wavelength, and it resolved the problem of the ultraviolet catastrophe. The formula was a triumph of mathematical ingenuity, but it was also a paradigm shift in how energy was understood. For the first time, a successful theory of radiation required the assumption that energy was not continuous but quantized. This brings us to the second key point: how Planck's hypothesis, though initially rejected and misunderstood, laid the foundation for the birth of quantum mechanics. While Planck's discovery was a major breakthrough, it was by no means the end of the story. The concept of quantized energy seemed to fly in the face of the prevailing views of classical physics. Even Planck himself had a hard time accepting the full implications of his own work. It wasn't until Albert Einstein applied Planck's theory to explain the photoelectric effect that the concept of energy quantization gained wider acceptance. Einstein's work on the photoelectric effect in 1905 provided compelling evidence for the quantization of energy. Einstein showed that when light of a certain frequency strikes a metal surface, electrons are ejected from the surface. Classical wave theory of light couldn't explain this phenomenon because it predicted that the energy of ejected electrons should depend on the intensity of the light, but instead it depended on the frequency. To explain this, Einstein proposed that light itself was quantized, existing in discrete packets of energy called photons. This was a direct application of Planck's idea of quantized energy, and it gave a physical reality to the concept of quanta. Although Einstein's work on the photoelectric effect established the importance of Planck's hypothesis, the scientific community remained reluctant to fully embrace quantum theory. The idea that energy was quantized was so counterintuitive that many prominent physicists, including some who had contributed to the development of classical physics, were hesitant to accept it. The leap from classical physics, which treated energy as continuous, to quantum mechanics, which treated energy as discrete, was too great a jump for many to make. Nevertheless, as the years passed, more and more experimental evidence accumulated that supported Planck's hypothesis. Niels Bohr, for example, developed his model of the atom based on Planck's concept of quantized energy levels. Bohr proposed that electrons and atoms could only occupy specific energy levels and that the transition between these levels resulted in the emission or absorption of radiation, again quantized. Bohr's work was another step toward the acceptance of quantum theory and demonstrated how the quantization of energy could explain previously puzzling aspects of atomic structure. In the 1920s, physicists like Werner Heisenberg, Erwin Schrödinger, and Paul Dirac further developed quantum mechanics into a fully fledged theory. Heisenberg's uncertainty principle, Schrödinger's wave equation, and Dirac's relativistic quantum theory built on Planck's original work and provided a comprehensive framework for understanding the behavior of particles at microscopic scales. The new theory not only explained radiation but also provided insights into the behavior of subatomic particles and interactions that classical physics could not. Thus, Planck's discovery of energy quantization was not just a mathematical curiosity, it was the beginning of a revolution in physics. Quantum mechanics, the theory that emerged from Planck's initial insight, has had far-reaching implications, not just for physics, but also for technology, chemistry, and even philosophy. Today, quantum mechanics is the foundation of much of modern technology, from computers and smartphones to lasers and MRI machines. The world of subatomic particles, governed by the rules of quantum mechanics, is vastly different from the classical world we experience, and it's through Planck's insight into energy quantization that we are able to unlock these secrets. In conclusion, Max Planck's hypothesis of quantized energy, though initially met with skepticism, was one of the most important discoveries in the history of physics. It challenged the classical understanding of the physical world and led to the birth of quantum mechanics, a theory that has had profound implications for both science and technology. While it may have seemed like a mathematical trick at first, Planck's discovery was the key to unlocking the mysteries of the quantum world, and it paved the way for the development of a new understanding of reality. It is through his work that we came to realize that the universe, at its most fundamental level, is governed not by smooth, continuous laws, but by discrete quantities that obey the strange and fascinating rules of quantum mechanics. Max Planck's revolutionary idea of energy quantization is one of the most pivotal moments in the history of science. However, it did not occur in a vacuum. The development of quantum mechanics was a long and often contentious process, one that involved many physicists built on Planck's work and challenging long-held beliefs about the nature of energy, light, and the universe itself. The true significance of Planck's discovery, though, only became clear as the scientific community began to piece together a new understanding of reality, one that would ultimately reshape not only physics but the technological landscape of the 20th century. To fully grasp the implications of Planck's work, we must explore how his discovery served as the spark that ignited the quantum revolution, starting with how his concept of quantization addressed the inadequacies of classical physics. Classical physics had a remarkable track record of explaining macroscopic phenomena, from the motion of planets to the behavior of gases. Isaac Newton's laws of motion, for example, described the movement of objects in our everyday world with astounding accuracy. James Clerk Maxwell's theory of electromagnetism unified the concept of electricity, magnetism, and light into one coherent framework. And yet, despite its successes, classical physics began to show signs of strain when faced with certain problems, such as blackbody radiation. In the late 19th century, scientists were puzzled by the problem of blackbody radiation, a phenomenon in which an idealized object absorbs all radiation that falls on it and emits radiation based on its temperature. Classical physics, when applied to this phenomenon, predicted that the energy emitted by the object would increase without bound at shorter wavelengths, leading to what was known as the ultraviolet catastrophe. The theory suggested that an infinite amount of energy would be emitted at high frequencies, which clearly didn't align with what was observed in experiments. Classical physics simply couldn't explain this anomaly, and the scientific community was at a loss for how to resolve it. Max Planck entered this scene in 1900, tasked with addressing the discrepancy between theory and experiment. He approached the problem by introducing a concept that would later become one of the most important ideas in the history of physics, the quantization of energy. Planck hypothesized that energy was not emitted or absorbed continuously, as classical physics suggested, but rather in small, discrete units, or quanta. This was a revolutionary idea that went against the grain of classical physics, which assumed that energy flowed smoothly and continuously. The concept of quantization was so radical that even Planck himself did not fully embrace it at first. He viewed it as a mathematical tool rather than a true description of nature. Planck's breakthrough came when he derived a formula, now known as Planck's law, which described the spectral distribution of radiation from a black body. His formula matched experimental data perfectly, providing an accurate description of black body radiation. While the mathematical success of Planck's law was undeniable, the physical interpretation of his work was far from settled. Planck himself had no clear understanding of why energy should be quantized, and he introduced the concept purely as a mathematical necessity. Nevertheless, Planck's formula solved the problem of blackbody radiation and marked the beginning of a new era in physics, even though the full implications of his work were not yet understood. The scientific community's reaction to Planck's work was mixed. Many physicists, particularly those deeply rooted in classical physics, were initially skeptical of the idea of quantized energy. The idea that energy could be divided into discrete packets rather than flowing continuously was difficult to accept, and many viewed it as an artificial construct rather than a real physical phenomenon. It wasn't until Albert Einstein applied Planck's concept to the photoelectric effect, 1905 that the idea of quantization began to gain more widespread acceptance. Einstein's work demonstrated that light, which had traditionally been viewed as a continuous wave, could also be treated as discrete packets of energy, or photons. This was a direct application of Planck's hypothesis, and it provided experimental confirmation of the idea that energy could indeed be quantized. However, despite the growing evidence for the quantization of energy, many scientists remained reluctant to fully embrace the implications of quantum theory. The idea of quantized energy was so counterintuitive that it took years for the full scope of its consequences to be understood. It wasn't until the 1920s when figures like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger developed the framework of quantum mechanics that Planck's discovery was fully integrated into a broader theory of the microscopic world. In the years following Planck's work, quantum mechanics would come to explain not only blackbody radiation but also atomic structure, chemical reactions, and the behavior of subatomic particles. The transition from classical to quantum physics was not smooth, and the road was fraught with philosophical debates and scientific resistance. Classical physics had provided a clear and deterministic view of the world, where every motion and interaction could be predicted with certainty. In contrast, quantum mechanics introduced a probabilistic view of the universe where particles could exist in multiple states at once, and their behavior could only be predicted in terms of probabilities. The strange and counterintuitive nature of quantum mechanics led to many philosophical questions about the nature of reality itself. Did particles have definite properties before they were measured? How could particles be in multiple states simultaneously? And perhaps most troubling of all, how could the behavior of individual particles be described by probability rather than certainty? These questions, while unsettling, were eventually answered through the development of quantum mechanics, a theory that is now one of the most successful and well-tested frameworks in all of science. Quantum mechanics has had a profound impact not only on physics but on other fields as well. In chemistry, quantum theory has explained the structure of atoms and molecules, leading to the development of new materials and technologies. In computing, the principles of quantum mechanics are being used to develop quantum computers which have the potential to revolutionize fields like cryptography, artificial intelligence, and optimization. One of the most important aspects of Planck's discovery was that it changed the way scientists thought about the relationship between energy and matter. Before Planck, energy and matter were treated as separate entities, with energy being a continuous variable that could be transferred in various ways. Planck's discovery demonstrated that energy was intrinsically linked to matter, and that it was the behavior of energy, whether it was emitted, absorbed, or transmitted, that determined the behavior of matter at the atomic and subatomic scales. This understanding was critical in the development of quantum mechanics, which treats particles as both waves and particles and describes their behavior in terms of probabilities rather than certainties. Planck's contribution to science, while initially met with resistance, ultimately reshaped our understanding of the universe. His discovery of quantized energy provided the foundation for the development of quantum mechanics, which has since become the bedrock of modern physics. Today, quantum mechanics is not just a theoretical framework. It is the basis for much of the technology that shapes our lives, from semiconductors to lasers, to the emerging field of quantum computing. Planck's legacy is not only one of intellectual achievement, but also one of enduring influence. As his discovery continues to inspire and guide the field of physics today, the implications of Planck's discovery extend far beyond the realm of theoretical physics. Quantum mechanics has had a profound impact on technology, medicine, and even philosophy. In technology, quantum theory has led to innovations like the transistor, the laser, and the development of computers and communication systems that rely on quantum principles. In medicine, quantum mechanics is at the heart of technologies like magnetic resonance imaging (MRI), which relies on the quantum properties of nuclei to produce detailed images of the human body. Philosophically, quantum mechanics has raised questions about the nature of reality, consciousness, and the limits of human knowledge. In conclusion, Max Planck's discovery of energy quantization was a momentous event in the history of science. It was the key that unlocked the mysteries of the microscopic world and paved the way for the development of quantum mechanics. Although his idea was initially met with skepticism and resistance, it ultimately transformed the way we understand the universe. Today, Planck's legacy lives on in the technologies we use every day, from computers to medical equipment, and in the scientific theories that continue to guide our exploration of the universe. Planck's work not only changed physics, but also changed the world. The birth of quantum mechanics, sparked by Max Planck's discovery of energy quantization, was not merely a mathematical solution to a specific problem. It was the beginning of a fundamental shift in our understanding of the universe. Planck's work on blackbody radiation laid the foundation for the entire quantum theory, but the true significance of his discovery would take time to be fully appreciated. It required the contributions of other physicists, such as Albert Einstein, Niels Bohr, and Werner Heisenberg, who expanded on Planck's insights and developed the framework that would change the way we perceive the physical world. To understand the profound nature of Planck's discovery, we must explore how it challenged classical physics, the philosophical implications it raised, and how it set the stage for the development of quantum mechanics. Classical physics, at the dawn of the 20th century, was seen as the unchallenged and reliable framework for understanding natural phenomena. The laws formulated by Isaac Newton for motion and gravity had been in place for centuries, successfully explaining the movements of celestial bodies and everyday objects. Likewise, James Clerk Maxwell's equations on electromagnetism provided a robust explanation for how electric and magnetic fields interacted and how light behaved as an electromagnetic wave. In essence, classical physics painted a picture of the universe governed by deterministic laws, where causes led to predictable effects. However, despite its success in explaining many aspects of the physical world, classical physics began to show its limitations, especially in explaining phenomena at the atomic and subatomic scales. One of the most glaring discrepancies in classical physics was its inability to account for the behavior of blackbody radiation. Black bodies are theoretical objects that absorb all incoming electromagnetic radiation and emit radiation of their own. Classical physics predicted that as the temperature of a black body increased, it would emit radiation at shorter wavelengths with increasing intensity. This would theoretically lead to infinite radiation intensity at ultraviolet wavelengths, a prediction that was at odds with experimental observation. This discrepancy became known as the ultraviolet catastrophe. At this juncture, Max Planck entered the scene, tasked with resolving the issue of blackbody radiation. Planck's approach was radical, because he did not attempt to fix classical theories, but instead proposed a completely new concept: the idea that energy was not emitted or absorbed continuously, as classical physics suggested, but rather in discrete packets or quanta. This was a revolutionary shift because it implied that energy was not a smooth, continuous variable, as had been assumed for centuries, but a collection of discrete, indivisible units. Initially, Planck introduced this idea as a mathematical tool to make his equations fit with experimental data. Planck himself was hesitant to fully embrace the idea of energy quantization, viewing it as a provisional step rather than a fundamental truth about nature. Despite Planck's own reservations, his mathematical formulation, known as Planck's law, perfectly described the observed spectrum of radiation from black bodies. The formula resolved the ultraviolet catastrophe and matched experimental data with astonishing accuracy. The significance of this achievement lay in the fact that Planck had solved a problem that classical physics could not, using a completely novel idea. The implication was that energy might not be continuous after all. This concept of energy quantization, while initially dismissed by many as a mathematical trick, would later become the cornerstone of quantum mechanics. Planck's discovery demonstrated that classical physics could not provide a complete explanation of the natural world, and that the universe, on a microscopic scale, behaved in ways that defied classical intuition. While Planck's discovery was a major breakthrough, its full implications were not immediately understood. Classical physicists were not ready to abandon their well-established beliefs, and the idea that energy could be quantized seemed absurd. Even Planck himself did not initially consider his theory as a true reflection of nature. It was only through the work of Albert Einstein in 1905, when he applied Planck's quantization to explain the photoelectric effect, that the concept of quantized energy gained wider acceptance. Einstein showed that light, traditionally considered a wave phenomenon in line with Maxwell's theory, could also be understood as being composed of discrete particles, or photons. When light of a certain frequency struck a metal surface, It caused the ejection of electrons, but only if the frequency of the light exceeded a certain threshold. Classical wave theory could not explain this, but Einstein's application of Planck's quantization to light provided a solution. This was a pivotal moment in the history of quantum mechanics, as it gave physical meaning to Planck's theory and demonstrated that energy quantization was not just a mathematical convenience, but a fundamental characteristic of nature. Einstein's work on the photoelectric effect was crucial in the development of quantum theory, but it was only one piece of the puzzle. Niels Bohr, building on Planck and Einstein's ideas, developed his model of the atom, in which electrons orbit the nucleus at discrete energy levels. This model explained the spectral lines of hydrogen, something that classical physics had struggled to describe. Bohr's model introduced the concept of quantum jumps, where electrons could move between discrete energy levels by absorbing or emitting photons, further solidifying the idea that energy was quantized. However, Bohr's model had its limitations, particularly in explaining the behavior of atoms with more than one electron, and it would later be superseded by more sophisticated models. As the 1920s progressed, quantum mechanics was refined by the work of physicists like Werner Heisenberg, who developed matrix mechanics, and Erwin Schrödinger, who introduced wave mechanics. These two approaches were later shown to be equivalent, but each contributed a different perspective on how to describe the quantum world. Heisenberg's uncertainty principle, which states that one cannot simultaneously know both the position and momentum of a particle with absolute precision, further challenged the deterministic view of classical physics. Schrödinger's wave equation, which describes the evolution of quantum systems, introduced the concept of probability wave, where particles do not have well-defined positions but rather exist in a range of possible locations until measured. These developments formed the foundation of modern quantum mechanics, which now underpins much of our understanding of the microscopic world. The philosophical implications of Planck's discovery and the development of quantum mechanics are profound. Classical physics, with its deterministic laws, offered a sense of predictability and control over the natural world. The notion that the universe could be understood through exact laws and calculations provided a sense of order. However, quantum mechanics shattered this certainty by introducing an inherent element of probability and uncertainty into the behavior of particles. At the quantum level, particles do not have well-defined properties until measured, and their behavior can only be predicted probabilistically. This shift from determinism to probability raised deep philosophical questions about the nature of reality. If particles do not have definite properties until observed, what does this say about the nature of existence? Is the universe fundamentally random? Or is there a deeper order that we do not yet understand? These questions were the subject of heated debates among physicists and philosophers alike. Albert Einstein, despite being one of the founders of quantum theory, famously disagreed with the probabilistic nature of quantum mechanics. His famous quote, "God does not play dice with the universe," reflects his belief that the apparent randomness in quantum mechanics was a sign that the theory was incomplete, and that a deeper, deterministic theory must exist. In conclusion, Max Planck's discovery of energy quantization was a key turning point in the history of physics. His work solved the problem of black-body radiation and laid the foundation for the development of quantum mechanics, which would revolutionize our understanding of the physical world. However, the full implications of Planck's discovery were not realized until the work of Albert Einstein, Niels Bohr, and other physicists who expanded upon his ideas. Quantum mechanics challenged the classical deterministic view of the universe and introduced a probabilistic framework that has had profound implications for both science and philosophy. Today, quantum theory is not only a cornerstone of modern physics, but also the basis for much of the technology that shapes our lives. The legacy of Planck's discovery continues to influence our understanding of the universe and our place within it. Max Planck's discovery of the quantization of energy stands as one of the most significant moments in the history of physics, triggering the eventual development of quantum mechanics. It represents not only a mathematical breakthrough but also a fundamental shift in the way humans understand the universe. However, to fully grasp the magnitude of this discovery, we must consider its implications in the context of the scientific landscape at the time and trace its evolution through the work of other groundbreaking physicists. Planck's discovery laid the foundation for the understanding of the atomic and subatomic world, and although it was initially met with skepticism, it opened doors to new realms of science that have revolutionized our technology, philosophy, and worldview. To fully appreciate this, we must explore how his discovery challenged classical physics, the shift it provoked in the scientific community, and how it ultimately led to the establishment of quantum mechanics, a framework that continues to shape our scientific and technological advancements. At the end of the 19th century, classical physics had already proven its worth in describing many physical phenomena. The laws of motion, developed by Isaac Newton, and the electromagnetic theory by James Clerk Maxwell had been integral in understanding the behavior of large objects and the interactions between light and matter. However, classical physics began to face challenges when confronted with certain phenomena, one of the most famous being the problem of black-body radiation. A black body is an idealized physical object that absorbs all incident radiation, regardless of frequency or angle, and re-emits that energy in a characteristic spectrum that depends on its temperature. Classical physics, particularly the Rayleigh-Jeans law, attempted to describe this spectrum, but it encountered a major flaw. It predicted that as the temperature of a black body increased, the radiation emitted would increase without limit at shorter wavelengths. This prediction led to the ultraviolet catastrophe, where the theory suggested that infinite radiation would be emitted in the ultraviolet region of the spectrum, something clearly not observed in experiments. The failure of classical physics to explain blackbody radiation signaled a fundamental flaw in its applicability to all phenomena. This gap in understanding created a pressing problem that demanded a new solution. Max Planck, a German physicist, entered this debate in 1900 with a radical proposal. Rather than adhering strictly to the classical theories, Planck introduced the idea of quantized energy. That is, energy is not continuous as had been assumed by classical physics, but rather exists in discrete packets, which he called quanta. Planck's approach to solving the problem was both mathematical and conceptual. He derived a formula, now known as Planck's law, that accurately described the observed spectrum of radiation emitted by black bodies at different temperatures. However, the truly revolutionary aspect of Planck's formula was the incorporation of the concept that energy was not emitted in a continuous flow, but in discrete units proportional to the frequency of the radiation. Planck's law explained the experimental data beautifully and resolved the ultraviolet catastrophe. His formula fit the data perfectly, providing a solution to a problem that had stymied physicists for decades. Despite this success, Planck himself was hesitant to fully accept the physical reality of energy quantization. Initially, he regarded the idea as a mathematical tool, a necessary assumption to make the math work and match the experimental results. He introduced the idea of energy quanta only because it made his formula work, but he did not yet believe it reflected the true nature of energy. This reluctance to fully embrace the implications of his own work showed the deep resistance to the concept of quantization that prevailed in the scientific community. Even Planck, the man who introduced the idea, did not initially grasp its full significance. The true importance of Planck's discovery only became clear through the work of other scientists, most notably Albert Einstein. In 1905, Einstein applied Planck's quantization of energy to explain the photoelectric effect, a phenomenon in which light shining on a metal surface causes the emission of electrons. Classical wave theory of light had failed to explain this effect, which was observed to depend on the frequency of the light, not its intensity. Einstein's application of Planck's theory showed that light itself could be described as being composed of discrete packets of energy, later called photons. This was a direct extension of Planck's quantization idea, and Einstein's work helped to establish the reality of energy quanta in nature. Einstein's work provided the experimental validation that Planck's theory had been lacking. The concept of quantized energy, initially introduced as a mathematical convenience, was now a well-supported physical reality. This was the beginning of the quantum revolution, and it was not just an isolated discovery but a fundamental shift in the way scientists understood energy, light, and the very nature of the universe itself. While Planck and Einstein laid the groundwork for quantum theory, it was Niels Bohr who took the next major step in the early 20th century. In 1913, Bohr developed a model of the atom that incorporated Planck's ideas of energy quantization. Bohr's model proposed that electrons in an atom occupied discrete energy levels, and that when an electron transitions between these levels, it absorbs or emits radiation in discrete amounts, corresponding to the energy difference between the levels. This idea was revolutionary because it provided an explanation for the spectral line observed in the hydrogen atom lines that classical physics could not explain. Bohr's atomic model was a critical extension of Planck's work. Bohr showed that quantization wasn't just limited to blackbody radiation or light. It applied to the behavior of electrons and atoms. This insight helped to establish the idea of quantized states not only in the realm of electromagnetic radiation, but in the very structure of atoms themselves. The evolution of quantum theory continued through the contributions of other physicists, including Werner Heisenberg and Erwin Schrödinger. Heisenberg's uncertainty principle, which stated that it is impossible to simultaneously know both the position, momentum of a particle with absolute precision, further challenged the deterministic worldview of classical physics. Schrödinger's wave equation, which described the evolution of quantum systems, introduced the concept of wave-particle duality, where particles like electrons could exhibit both particle-like and wave-like behavior depending on the circumstances. These advances culminated in the fully developed theory of quantum mechanics, which succeeded in explaining phenomena at the atomic and subatomic level with unprecedented accuracy. Quantum mechanics was radically different from classical physics in its treatment of the physical world. Classical physics had been based on the assumption that the universe was deterministic, governed by precise laws that allowed the prediction of future events. In contrast, quantum mechanics introduced the concept of probability, where the behavior of particles could only be predicted in terms of probabilities, not certainties. This probabilistic view of the universe was a direct result of Planck's initial discovery and the subsequent work of Einstein, Bohr, Heisenberg, and Schrödinger. The philosophical implications of quantum mechanics were profound. The idea that particles do not have definite properties until they are measured and that their behavior is governed by probabilities challenged long-held beliefs about the nature of reality. Was the universe truly indeterminate at its most fundamental level? Or was this simply a result of our inability to measure everything precisely? The philosophical debates about the implications of quantum mechanics continue to this day. Quantum mechanics not only changed our understanding of the physical universe but also transformed technology. The principles of quantum theory are at the heart of many technologies that shape our modern world, including semiconductors, lasers, and magnetic resonance imaging (MRI). The development of quantum computing, which relies on the principles of quantum mechanics to perform calculations far beyond the capability of classical computers, promises to revolutionize fields like cryptography, artificial intelligence, and optimization. In conclusion, Max Planck's discovery of energy quantization was the key that unlocked the mysteries of the atomic and subatomic world. It was a concept that challenged classical physics, revolutionized our understanding of the universe, and paved the way for the development of quantum mechanics. While Planck himself did not fully embrace the implications of his work, his discovery laid the foundation for the groundbreaking contributions of Einstein, Bohr, Heisenberg, and Schrödinger, whose work ultimately established quantum mechanics as the dominant theory of the microscopic world. Today, Planck's legacy lives on in both the science that underpins our understanding of nature and the technology that shapes our modern lives. Max Planck's discovery of the quantization of energy was groundbreaking, but the true magnitude of his work was not immediately understood. His introduction of the idea that energy could only exist in discrete packets or quanta fundamental challenged classical physics, which had long assumed that energy was a continuous quantity. This radical shift in understanding marked the beginning of the quantum revolution. But the journey from Planck's hypothesis to the fully developed theory of quantum mechanics involved contributions from other brilliant minds, such as Albert Einstein, Niels Bohr, and Werner Heisenberg. At the time of Planck's discovery, classical physics was the dominant framework for explaining the physical world. Newton's laws of motion and Maxwell's electromagnetic theory had been incredibly successful in describing the behavior of macroscopic objects and electromagnetic waves respectively. However, when it came to explaining the radiation emitted by heated objects, particularly blackbody radiation, classical physics failed. This problem known as the ultraviolet catastrophe, occurred because classical physics predicted that as the temperature of a black body increased, its radiation would become infinitely intense at short wavelengths. Experimental data, however, showed that this was not the case. Planck, seeking to solve this problem, proposed that energy was not emitted or absorbed continuously but in discrete units. Initially, he introduced this idea purely as a mathematical tool to make his equations work, but his law of radiation perfectly matched experimental observations, offering a solution to the ultraviolet catastrophe. This was a crucial moment in physics, as it suggested that classical theories were inadequate for explaining the behavior of energy on the microscopic scale. However, the idea of quantized energy was so counterintuitive that even Planck himself was hesitant to accept its full implication. He viewed the concept as a temporary solution, not a physical reality. It wasn't until Albert Einstein applied Planck's theory to the photoelectric effect in 1905 that the concept of energy quantization gained widespread acceptance. Einstein showed that light, which was traditionally seen as a continuous wave, could also be understood as being made of discrete packets of energy called photons. This work demonstrated that Planck's hypothesis was not just a mathematical convenience, but reflected a fundamental property of nature. Following Einstein's work, Niels Bohr extended Planck's ideas to the structure of the atom. In his 1913 model of the hydrogen atom, Bohr proposed that electrons could only occupy specific, discrete energy levels, and when they transitioned between these levels, they emitted or absorbed quantized amounts of energy. This was a direct application of Planck's quantization and provided a way to explain the discrete lines in the hydrogen spectrum that had been puzzling scientists for years. Bohr's model was a major step in the development of quantum mechanics, but it also had its limitations, particularly in explaining the spectra of more complex atoms. The further development of quantum theory came in the 1920s when physicists like Werner Heisenberg and Erwin Schrödinger developed the full framework of quantum mechanics. Heisenberg introduced the uncertainty principle, which stated that it is impossible to simultaneously measure the exact position and momentum of a particle, while Schrödinger formulated the wave equation, which described the probabilistic behavior of particles. These contributions, along with the work of Planck, Einstein, and Bohr, formed the basis of quantum mechanics and provided a comprehensive understanding of the behavior of matter at the atomic and subatomic levels. Today, quantum mechanics has become the foundation of modern physics. It has had profound implications for technology, from semiconductors to lasers, and is central to emerging fields like quantum computing. The development of quantum mechanics was a long and difficult journey, but it all began with Planck's simple but profound idea that energy exists in discrete quantities. This idea, though initially met with skepticism, laid the groundwork for one of the most successful and transformative theories in the history of science. Max Planck's discovery of energy quantization in 1900 marked a pivotal moment in the history of physics, challenging the well-established principles of classical mechanics. At the time, classical physics, which had been immensely successful in describing large-scale phenomena, was being stretched to its limits when it came to understanding the behavior of radiation. Specifically, classical theory failed to explain black-body radiation, a key area of study that sought to understand how objects emit radiation based on their temperature. The discrepancy between classical predictions and experimental data led to what was known as the ultraviolet catastrophe, where classical physics predicted an infinite amount of radiation at short wavelengths, which contradicted observation. Planck's solution to this problem was both simple and revolutionary. He proposed that energy was not emitted or absorbed continuously, as classical physics assumed, but in discrete packets, or quanta. Planck's hypothesis was groundbreaking because it implied that energy, rather than being a smooth and continuous variable, was instead composed of discrete units. Initially, Planck introduced this idea purely as a mathematical necessity, a tool to make his equations fit with experimental data. He did not fully believe that energy was fundamentally quantized, but his law of radiation, which matched the experimental data perfectly, solved the problem of the ultraviolet catastrophe and provided a new way of thinking about energy. His formula, now known as Planck's law, became a cornerstone of quantum theory. Though Planck's discovery was a monumental achievement, it faced considerable skepticism from the scientific community. The concept of energy being quantized went against the principles of classical physics, which had dominated scientific thought for centuries. Even Planck himself hesitated to embrace the full implications of his discovery, viewing it as an anomaly rather than a new reality of nature. It wasn't until Albert Einstein's work on the photoelectric effect in 1905 that the idea of quantized energy gained broader acceptance. Einstein applied Planck's quantum hypothesis to explain the photoelectric effect, where light striking a metal surface caused the emission of electrons, by showing that light, traditionally seen as a wave, could also be described as being made of discrete packets of energy, photons. Einstein's work provided concrete evidence for the reality of energy quantization. Niels Bohr also played a critical role in expanding Planck's ideas in the early 20th century. In 1913, Bohr developed his model of the atom, incorporating Planck's idea of quantized energy. Bohr proposed that electrons in atoms could only occupy discrete energy levels, and when electrons moved between these levels, they would emit or absorb energy in specific amounts. This explained the discrete spectral lines observed in atomic spectra, and provided further confirmation of Planck's hypothesis. Bohr's model of the atom was a breakthrough in understanding atomic structure, and it marked the beginning of a new era in atomic physics. The development of quantum mechanics in the 1920s, through the work of physicists such as Werner Heisenberg, Erwin Schrödinger, and Paul Dirac, marked the culmination of Planck's discovery. Heisenberg's uncertainty principle, which stated that it was impossible to precisely measure both the position and momentum of a particle simultaneously, challenged the deterministic worldview of classical physics. Schrödinger's wave equation introduced the concept of wave-particle duality, where particles like electrons exhibit both wave-like and particle-like properties. These developments formed the basis for modern quantum mechanics, a theory that has become central to our understanding of the microscopic world. Today, quantum mechanics has transformed many areas of science and technology, from semiconductors and lasers to quantum computing. The principles of quantum theory are at the heart of modern technological innovation. The journey from Planck's initial insight into energy quantization to the fully developed theory of quantum mechanics is a testament to the power of scientific progress. Planck's discovery, though initially controversial, laid the groundwork for a revolutionary shift in our understanding of the universe, one that continues to influence the course of scientific inquiry today. Max Planck's discovery of energy quantization stands as one of the most transformative moments in the history of physics. In the late 19th century, classical physics, which had been incredibly successful in describing macroscopic phenomena, faced serious challenges in explaining certain microscopic phenomena. One such problem was black-body radiation, where classical theory, particularly the Rayleigh-Jeans law, predicted that radiation would increase indefinitely at short wavelengths, an outcome known as the ultraviolet catastrophe. However, experimental data showed that this was not the case, as the intensity of radiation peaked and then declined at shorter wavelengths. This gap between theory and experiment prompted Max Planck to develop a new solution. Planck's resolution to this problem was groundbreaking. He proposed that energy is not emitted or absorbed continuously, but in discrete packets, which he termed quanta. This was a radical departure from classical physics, which had assumed that energy could be divided infinitely into smaller parts. Planck's idea, though initially introduced as a mathematical necessity, suggested that energy came in fixed units, depending on the frequency of radiation. His formula for black-body radiation, now known as Planck's law, perfectly matched experimental data and resolved the ultraviolet catastrophe. This was the beginning of a new era in physics, though Planck himself did fully grasp the deeper implications of his discovery at the time. Despite the mathematical success of Planck's law, the concept of quantized energy was difficult to accept within the scientific community. At the time, classical physics reigned supreme, and the idea that energy could be divided into discrete quanta was difficult for many scientists to comprehend. Planck himself initially viewed the quantization of energy as a temporary solution to a problem rather than a fundamental shift in understanding. The scientific community, too, was slow to accept the implications of this new idea. It wasn't until Albert Einstein's work on the photoelectric effect in 1905 that the concept of energy quantization began to gain more widespread acceptance. Einstein's groundbreaking work demonstrated that light, traditionally considered a continuous wave, could also be understood as a collection of discrete packets of energy called photons. His explanation of the photoelectric effect, in which light, striking a metal surface, causes the emission of electrons, relied on the idea of quantized energy. This was a critical validation of Planck's hypothesis, and it marked the beginning of the quantum revolution. Einstein's work showed that energy quantization was not just a mathematical artifact but a physical reality, bridging the gap between theory and experiment and solidifying Planck's discovery. The development of quantum mechanics was further advanced by Niels Bohr, who, in 1913, incorporated Planck's concept of quantization into his model of the atom. Bohr's model proposed that electrons in an atom could only occupy discrete energy levels, and that the emission or absorption of energy occurred when electrons transitioned between these levels. This explained the discrete spectral lines observed in atomic spectra, providing further experimental confirmation of the quantization of energy. Bohr's work, though revolutionary, also had its limitations, particularly when it came to explaining atoms with more than one electron. Nevertheless, his model was a crucial step in the development of quantum mechanics. As the 1920s progressed, the development of quantum mechanics accelerated with the contributions of Werner Heisenberg, Erwin Schrödinger, and Paul Dirac. Heisenberg introduced the uncertainty principle, which stated that it is impossible to simultaneously measure both the position and momentum of a particle with absolute precision. This principle shattered the deterministic worldview of classical physics, where it was assumed that all properties of a system could be known exactly. Schrödinger, on the other hand, formulated the wave equation, which described the probabilistic behavior of quantum particles. The wave equation introduced the idea of wave-particle duality, where particles could exhibit both particle-like and wave-like properties depending on how they were observed. These developments culminated in the fully realized theory of quantum mechanics, a framework that revolutionized not only physics but also many areas of science and technology. Quantum mechanics provided a new understanding of matter and energy at the atomic and subatomic scales, where classical physics no longer applied. The theory had profound implications for our understanding of the universe, leading to innovations such as semiconductors, lasers, and quantum computers. The development of quantum mechanics, while rooted in Planck's initial insight, was the result of decades of work by many brilliant physicists who extended and refined his ideas. Today, quantum mechanics remains one of the most successful and well-tested theories in science. It continues to shape our understanding of the natural world and has become the basis for numerous technological advancements that have transformed our daily lives. From the microchips that power our computers to the lasers used in medical treatments, quantum mechanics is at the heart of many of the technologies that define the modern world. Planck's discovery, though initially met with skepticism, set the stage for the development of one of the most powerful and transformative theories in the history of science. Max Planck's discovery of energy quantization in 1900 was a pivotal moment in the history of physics, revolutionizing our understanding of the microscopic world and laying the foundation for the development of quantum mechanics. Planck's work challenged the established laws of classical physics, offering a radical new perspective that led to the birth of quantum theory and changed the course of science forever. His discovery not only solved a critical problem in the understanding of radiation, but also introduced the idea that energy is not continuous but exists in discrete units, or quanta. While initially a theoretical proposition, Planck's hypothesis would go on to become a cornerstone of modern physics. The context in which Planck made his discovery is essential to understanding its significance. Classical physics, at the turn of the 20th century, had been highly successful in explaining the behavior of large-scale objects, from the motion of planets to the behavior of light. However, when it came to explaining phenomena at the atomic and subatomic levels, classical physics began to show its limitations. One such problem was the study of black-body radiation, which describes how objects emit radiation based on their temperature. Classical physics, particularly the Rayleigh-Jeans law, predicted that radiation would increase infinitely at shorter wavelengths, leading to what was known as the ultraviolet catastrophe. This prediction clearly contradicted experimental observations, creating a major problem for scientists. Planck, in his pursuit to resolve this issue, proposed that energy was not emitted or absorbed continuously, as classical theory suggested, but in discrete units. This was the birth of the concept of quantized energy. While this idea was a radical departure from the continuous nature of energy that classical physics had embraced, Planck's mathematical formula, known as Planck's law, successfully described the observed radiation from black bodies. His formula perfectly matched the experimental data, solving the ultraviolet catastrophe and providing an accurate description of blackbody radiation. Initially, Planck himself did not fully accept the physical reality of quantized energy. He introduced this idea as a mathematical tool to make his equations work, but he remained skeptical of its true nature. It wasn't until Albert Einstein applied Planck's hypothesis to the photoelectric effect in 1905 that the concept of quantized energy gained wider acceptance. Einstein showed that light, which had been understood as a continuous wave phenomenon, could also be described as being made up of discrete packets of energy, later known as photons. This was a critical validation of Planck's hypothesis and provided strong evidence that energy quantization was a real and fundamental property of nature. The development of quantum mechanics was further propelled by Niels Bohr, who, in 1913, incorporated Planck's ideas into his model of the atom. Bohr proposed that electrons in an atom could only occupy discrete energy levels, and that transition between these levels would result in the emission or absorption of energy in discrete amounts. This explained the observed spectral lines in hydrogen atoms, which had previously been a mystery. Bohr's model helped solidify the idea of quantized energy in atomic systems, demonstrating that Planck's hypothesis was not limited to radiation but applied to the very structure of atoms themselves. In the 1920s, the work of Werner Heisenberg, Erwin Schrödinger, and others led to the formalization of quantum mechanics. Heisenberg introduced the uncertainty principle, which states that it is impossible to simultaneously measure both the position and momenta of a particle with perfect accuracy. Schrödinger formulated the wave equation, which described the probabilistic nature of particles at the quantum level. These developments completed the framework of quantum mechanics, with Planck's idea of energy quantization at its core. The theory not only explained the behavior of light and atoms, but also provided a new way of thinking about the fundamental nature of matter and energy. Today, quantum mechanics remains the foundation of modern physics, explaining phenomena from the behavior of elementary particles to the functioning of complex technologies like semiconductors, lasers, and even quantum computers. Planck's discovery, though initially met with skepticism, has had profound implications for both science and technology. His insight into energy quantization laid the groundwork for a new understanding of the universe, one that has reshaped our view of reality itself. The impact of his work continues to be felt in countless fields, from particle physics to material science, and his legacy is a testament to the power of scientific innovation.